This video is to help complete the pre-lab for the Gas Concepts lab. So you can see there are 4 pre-lab questions on page 69. And what I'm going to do, or what I've made, is similar questions that require the same steps. So I'm going to go ahead and work through these created questions, and you're going to use the same process, the same steps, to work through the actual pre-lab questions. So let's look at the first question. Write a reaction if calcium reacted with hydrochloric acid. This is a single displacement reaction. So in order to do this, you need to first start by writing down the 2 reactants, and they are calcium with hydrochloric acid. So calcium is a metal, so it exists by itself. Now I would guess that it's most likely going to be in solid form, but since it doesn't specify, I'm not going to include its state of matter. Next, I write what it's reacted with by adding a plus sign. Now hydrochloric acid, looking up that chemical formula, is HCl. Now hydrochloric acid we're never going to use in a liquid form. What I mean by liquid form is it's never going to be 100% hydrochloric acid. That would be too strong. We're always going to have a diluted hydrochloric acid. So it would be aqueous. Now, we have to figure out the products, and to figure out the products, or to predict the products, knowing that it's a single displacement reaction is going to help us, because we have that scale A plus BC is going to make AC plus B. So A being calcium, the B being the hydrogen, and then the C being the chlorine. So in a single replacement reaction, what we have is A taking the place of B, knocking it out, so that A is paired with C on the product side, and then B is now by itself. So in order to figure out what these products look like, we need to write down all of the elements and their probable charges. So calcium's by itself on the reactant side, and when we have an element by itself, its oxidation state is 0. But what I'm going to write down here is what would be its oxidation state if it was in an ionic compound. And in order to figure that out, we need to look at where calcium is on the periodic table. So calcium is in group 2. It's an alkali earth metal. All alkaline earth metals form a +2 charge in an ionic compound. So if calcium, once it pairs up with another element in an ionic compound, it will have a +2 charge. Now looking at HCl, what charges do each of those atoms have? Well, hydrogen, looking at where it is on the periodic table in group 1 here, it's going to have a +1 charge. It's the cation in this case. Now chlorine, what it's partnered with, is a halogen, and all halogens form a -1 charge. So this helps me because once I switch partners, I'm going to need to know the oxidation states. I'm going to need to know the charges in order to predict the products. We said that calcium is going to take the place of hydrogen. A is going to kick out B, so that on the product side we have A, calcium, with C, in this case, chlorine. And then we're going to have hydrogen, B, by itself. But to figure out what these look like, we use the charges to figure it out for the ionic compound, using that crisscross method, where you take this 2 and it becomes a subscript on the chlorine, and then this 1 becomes a subscript on the calcium. So we need 1 calcium and 2 chlorines, giving us the formula CaCl2. Now for hydrogen, well, hydrogen when it's by itself, what does that look like? It's not going to have a positive charge anymore because it's an element by itself. It's going to be neutral. Well, this is where we have to remember those 7 diatomics on the periodic table. Hydrogen is one of those 7. What that means is when hydrogen exists in nature, it appears as a diatomic. So 2 hydrogen atoms come together and form a bond to become more stable. 1 hydrogen atom by itself isn't stable enough, so it pairs up with a second one, forming H2. So this is going to be the reaction. We need to make sure to balance it. So we need to make sure we have the same amount of atoms on both sides of the equation. So looking here, I have 1 calcium on the reactant side, 1 calcium on the product side. Next, going to hydrogen. 1 hydrogen on the reactant side, 2 hydrogens on the product side. So that means I need 2 on the reactant side, so I put a coefficient of 2 here to make 2 hydrogens on both sides. That also makes 2 chlorines on the reactant side, which I needed because I have 2 chlorines on the product side as well. So now this is a balanced chemical reaction. So using that balanced chemical reaction, I can try to solve number 2. Number 2 says, using the above reaction, and it needs to be balanced, if you have 1.87 grams of calcium reacted with excess hydrochloric acid, what amount of hydrogen gas would theoretically be emitted at STP? Okay, so this is a lot of information. It's kind of a difficult question to answer. So in order to figure this out, what it's asking us to solve for is the amount of hydrogen gas, so this guy here, in milliliters. So it's asking for the volume of hydrogen gas. So to figure that out, we're going to be using the ideal gas equation. PV is equal to nRT. Using this equation, P is the pressure in ATM, V is volume, and it's going to come out in liters. So notice we need it in milliliters when we solve, so we will have to convert. N is the number of moles. R is a gas constant given to you. Same for every time we use this equation. Leave the units off of that for now. And then temperature, T, is measured in Kelvin. So it doesn't look like it gave us enough information to solve, but it really did because of this STP. So what STP means is standard temperature and pressure. So by saying the words, or giving us the letters STP, it's telling us that the temperature we should be using is 273 Kelvin, and the pressure, standard pressure, is 1 atm. So we have the temperature, we have the pressure, and we have the R value. So the only 2 variables we don't have are N, the number of moles, and V, the volume. Well, V, we know that's what we're solving for. So this is our question mark. We're going to rearrange the equation to solve for volume. So that must mean that we should be able to figure out moles using the information given in this question. But how are we going to figure out moles? Well, let's see what else they gave us other than these STP conditions. They gave us 1.87 grams of calcium. So we have 1.87 grams of calcium. And what we're trying to figure out is volume of hydrogen gas. Well, in order to figure out volume of hydrogen gas, we need moles. So our goal here is to get from grams of calcium to moles of hydrogen gas. And to do this, we can use stoichiometry. We learned about stoichiometry yet in lecture. Stoichiometry is using a balanced chemical equation, and that's what this is up here, a balanced chemical equation, to convert from moles of one reactant or product to moles of a different reactant or product. And the way we can do this is because the coefficients, the numbers in front of each element or compound, represent the number of moles of that element or compound. So in this specific balanced chemical reaction, when there is no coefficient, we assume it's a 1. So what that's saying is we have 1 mole of calcium reacting with 2 moles of hydrochloric acid, and that is producing 1 mole of calcium chloride and 1 mole of hydrogen gas. In order to compare the calcium to the hydrogen gas, we need first to get this gram amount, 1.87 grams, into moles, because we can only use these coefficients, these molar amounts, if they're both in moles. So we have a middle step here. We need to get to moles of calcium, and that will allow us to get to moles of hydrogen, and this value is our N value that we can plug into that equation. So let's look at the setup and figure out what we need to solve. So here are our steps. We have grams of calcium. We need to get to moles of calcium. Whenever we convert between grams and moles, we use molar mass. Once we have moles of calcium, we need to get to moles of H2. To figure that out, we're using our balanced chemical equation, using the coefficients in front of both. So this is called a mole ratio. So 1 mole of calcium will produce 1 mole of H2. So it's a 1-to-1 mole ratio. So that makes that step easy. So I'm going to write the two pieces, the two conversion factors I need for these two steps over here, so I have them ready when I start my dimensional analysis. So for the first step, to go from grams of calcium to moles of calcium, I need the molar mass. Molar mass of calcium I get from my periodic table. And that is equal to 40.08. So in case you're wondering what I'm looking at, I find calcium on the periodic table, and this number underneath the symbol, 40.08, that's the molar mass of calcium. And when we find molar mass is measured in grams per mole. That's why we can use it to get between grams and moles. For the second step, I need the mole ratio, and we just said it was a 1-to-1 mole ratio. So what that means is, I'm running out of room here, 1 mole of calcium will produce 1 mole of H2. So if I set up my dimensional analysis, what I'm going to start with in this first step is that 1.87 grams of calcium. I then use my molar mass to convert between grams of calcium to moles of calcium. I put the 40.08 grams in the bottom so that they're on opposite sides of this horizontal line and they cancel. That'll put my 1 mole of calcium on the top, so the mole portion of the molar mass. Canceling out grams of calcium. If I stopped at this step, I would have moles of calcium. But I'm not going to stop at that step. I need to get all the way to moles of H2. For that, I'm using the mole ratio, which was 1-to-1. So 1 mole of H2 is going to be produced when 1 mole of calcium is used. Making moles of calcium cancel. Made my railroad tracks too big here. So multiply what's on the top. So 1.87 times 1 times 1. divided by what's on the bottom, 40.08. So this gets me 0.0666, a whole bunch of numbers after that. So this is moles of H2. So this is my N value that I'm using here. Notice I'm not worrying about sig figs because this isn't my final answer. Since I'm running out of room, let me bring in another sheet of paper to finish this example. So we did all of this work to get our moles because we needed all of the variables except for V, because V is what we're solving for using the ideal gas equation. So I'm going to take this ideal gas equation, PV is equal to nRT, and we're solving for volume. So I'm going to isolate volume and get it by itself. To do that, I divide both sides of the equation by P. P cancels out on this side, giving me volume is equal to nRT over P. Now I plug in all the values that I have. My molar amount of 0.04666. My R value, the gas constant, 0.08206. My temperature, which was standard temperature, 273 Kelvin. And then I divide that by my pressure, which standard pressure is 1 atm. I get a volume of 1.04529, etc., etc., etc. Okay, but what we're trying, this is our final answer, so we do want to worry about sig figs. And the only significant figures that matter are the ones in the initial problem. So we have 3 sig figs in the initial problem. We want 3 sig figs in the final answer. So it's going to be 1.0, and I have to round up because we look to the number next to it. If it's 5 or higher, it rounds up. So 1.05. But then we want to take note of our units. We just said that volume, when using this ideal gas equation and this R constant, is going to be liters. What did it ask for the answer in? Milliliters. So we need to convert this to milliliters. So 1.05 liters to milliliters, we need a conversion factor. And we have, you can use this memorized conversion factor, or you can just move the decimal point 3 times, whichever way you learned or know best. I'm going to show the conversion factor method. So the conversion factor 1000 milliliters is equal to 1 liters. I set up my dimensional analysis, starting with the number I'm trying to convert. I put the liter portion diagonally, that's why it's called dimensional analysis, so that the liter units cancel. And then I put the 1000 milliliters on the top. This is going to give me, I should be able to just move that, 050, there we go. 1050 milliliters. So all of that work for that final answer. All right, let's look at the next problem. So the next problem is if you have, in an experimental reaction, you have 28.5 milliliters collected of hydrogen gas at 27.2 degrees Celsius and 725 torr. What would be the volume corrected? So this is something that you're going to be doing in part A of the lab. You're going to have to calculate the corrected volume to STP conditions. So when you have to do a corrected volume, you're going to be using the combined gas law. And there is an equation sheet in the supplemental material folder that has these equations for you. So the combined gas law is P1V1 over T1 is equal to P2V2 over T2. So how do I know that that's the equation I'm going to be using? Because they're giving you a volume, that's what this is, volume, they're giving you a temperature, T1, and torr is a pressure, so this is a P1. So they're giving you volume, temperature, and pressure, and they're asking you to correct it to a different volume, pressure, and temperature. So that means you have two of each, and this is the only equation on that sheet that has two pressures, two volumes, two temperatures. So the P1 V1 over T1, this side is my experimental values, and this side, the P2 V2 T2, will be my STP conditions. So I'm going to make a list of my variables so that once I rearrange this equation, I can plug them in. So I have my experimental P1 is given here. Pressure, 752.5 torr. My experimental volume, 28.5. My experimental temperature, okay, now let's look at STP. So I'm going to write that list down here. So my P2, since we said standard temperature pressure, and remember from up in this problem, standard pressure was 1 atm, standard temperature was 273. And it's asking what would be the corrected volume. So it's asking what would be the volume at standard pressure and standard temperature. So that's my question mark. That's what I'm solving for. So I'm going to go ahead and rearrange this equation to solve for V2. And then before I plug in any of my variables here, I'm going to make sure that my units are fine. So let's rearrange this to solve for V2. So I need V2 by itself. So I get rid of the P2 and the T2. To do that, I multiply by the reciprocal. So if you don't know what that means, it means I'm going to take this is a fraction, P2 over T2, and flip it. So I'm going to take T2 over P2. So this is the reciprocal right here. So by multiplying by the reciprocal, what I'm doing is I'm canceling out P2, because they're now on opposite sides of the horizontal line. P2 divided by P2 cancels. And then it also cancels out my T2, leaving V2 by itself. Since I multiplied this side of the equation by T2 over P2, I need to do the same to this side. So I have V2 by itself because everything else canceled. And then on this side, I'm going to combine that. So in the numerator, I'm going to have T2, P1, and V1. In the denominator, I'm going to have just the P2 and the T1. So it's all set up now for me to plug in. But before I plug in, I need to check my units. And for this one, temperature is the only unit that absolutely has to be in Kelvin, because Kelvin's an absolute scale. We can't use degrees Celsius or degrees Fahrenheit for temperature because that's not an absolute scale. Fahrenheit and Celsius are in degrees because they can go negative. We need an absolute scale when we are using values for these variables. For pressure and volume, the units don't matter as long as the units are consistent between both. What I mean by that, my pressure, if I'm going to have it in torr, that's fine, but I need it in torr for both of my P values. So notice I have one pressure in torr, the other in ATM. So I need them to be consistent. Well, 1 ATM is equal to 760 torr. So that's an easy conversion. So if I get this pressure in torr, now they're both in the same units and I can leave them in torr. Now let's look at our volume. I can leave my volume in milliliters. All that means is once I calculate V2, it's also going to be in milliliters. For temperature, I just said it has to be in Kelvin. It has to have that absolute Kelvin scale. So I need to convert this top one, since it's in Celsius, into Kelvin, and I do that by adding 273 to it. So 27.2 plus 273 gives me 300.2 Kelvin. All right. So now my units are consistent. Torr, milliliters, it'll come out in milliliters, Kelvin, Kelvin. So now I can plug in. V2 is going to equal my T2, which is 273. Multiply that by P1, we got up here, 752.5, times my V1, 28.5. Divide that whole thing by P2, so going down here for P2, making sure I'm using the torr amount since my other pressure is in torr, times my T1, where is that? 300.2. Calculating that out. Please check my calculations. I'm sitting here talking, I sometimes press the wrong button and I'll get an incorrect answer, so let me know so I can alert other students if I do a calculation wrong. 25. Did I get 25.66? How many sig figs are we looking at? We have 3 there, 4 there. Choose the smallest, so we want 3. So 25.7, and since milliliters was used for the V1, we need to stick with milliliters for V2. So corrected volume to STP conditions should be 25.7 milliliters. Just double checking my calculations to make sure that's right. I got the same thing, so yes. All right, so that takes care of the first 3 on your pre-lab. For the 4th one, it asks you to write the balanced reaction for the experiment that you will actually be doing in part A, and that's actually given to you if you read the procedure. So hopefully you get that one right. The last question is referring to part B. So these other calculations are going to help you with part A that we did. For part B, it's asking, for the experiment to work, what must be the relationship of the boiling point of the unknown liquid to that of water? Okay, so if you watch the part B video, that is answered in that video when we talk about the definition of a volatile liquid.